Welcome back to this lecture series on pulse width modulation for power electronic converters. So, we have covered quite a few modules up to this point of time. We have had an overview of various power electronic converters, and we, with a particular focus on the voltage source converter, we looked at different applications of voltage source converters such as motor drives, active front end rectifiers, active power filters and so on. And then after this brief overview of the power converters and their applications, we started off with the basic purpose of pulse width modulation, namely to control the fundamental voltage and to mitigate the harmonics and their undesirable effects. So, we had a review of Fourier series and then the effect of different waveform symmetries etc. during that module. Then subsequently we went to pulse width modulation at low switching frequency. So, we considered very low switching frequencies such as one switching angle or two switching angles in every quarter, and then we tried to see how with just two switching angles we can control the harmonics and so on and so forth. And from that we went on to selective harmonic elimination and offline optimized PWM. And these portions, and subsequently we moved towards real time PWM, real time generation of PWM, which is what is most commonly done. And again it is not at low frequency, but at frequencies much higher than the fundamental frequency. So, something like if you are looking at a motor drive that would work up to 50 hertz fundamental frequency, we are looking at a switching frequency something like of a few kilohertz, like 5 kilohertz or 3 kilohertz or 8 kilohertz and so on and so forth. So, these two modules we have been looking at generation of PWM at where the switching frequencies are fairly higher than the fundamental modulating frequency, and here the generation is kind of based on triangle comparison, that is you use 3-phase modulating signals and compare them with a common triangular carrier and you produce PWM waveform. And this is an alternative approach which is space vector based PWM, and we showed that the space vector based PWM is more general than triangle comparison PWM. Many continuous PWM and discontinuous PWM methods are there, and those PWM waveforms can be generated either using the triangle comparison approach or the space vector approach. There are certain advanced space vector based bus clamping PWM techniques. Those advanced bus clamping PWM techniques, those PWM waveforms pertaining to them can be generated only in the space vector approach and not using the triangle comparison approach. And this after dealing with the PWM generation at high frequencies, at switching frequencies much higher than the fundamental frequency, we have been looking at the analysis of the line current ripple. We have started looking at the harmonic content of those waveforms, which basically determine the waveform quality. So, in the last lecture we had an overview of the harmonic spectra. So, we have actually had after a review of PWM techniques, we looked at what is the maximum fundamental voltage or the DC bus utilization with the various methods. So, if the DC bus voltage is VDC, the peak phase fundamental can be 0.5 times VDC for sine triangle, and with most of the other methods with common mode injection and so on, and the space vector based PWM methods, the the DC bus utilization can be increased by 15% now. And we also looked at the typical harmonic spectra corresponding to sine triangle PWM and so on, and the harmonic model. So, we would quickly revisit today how the typical voltage harmonic spectra would look like for a PWM technique, which is maybe based on triangle comparison or space vector, but where the switching frequency is much higher than the fundamental frequency. And we would look at the harmonic, we would quickly review the harmonic model, how an induction motor is seen by a harmonic voltage source or the harmonic components in the applied voltage, and we would look at the total harmonic distortion factor. After a quick review of these, we would go into the topic of the day, namely the error voltage vector. As I was mentioning the other day, that is the previous lecture when I was beginning with this. So, this error voltage vector is nothing but all these harmonics that you have other than the fundamental, all the harmonics. So, these harmonics or some of the harmonics you can call it as voltage ripple, and the 3-phase voltage ripple transformed into the space vector domain is the error voltage vector. So, we would have a discussion on this error voltage vector, and from then on we would move towards what is called a stator flux ripple vector, which would be our main focus of these things would be the main focus of our lecture today. And what is the stator flux ripple vector? It is the integral of error voltage vector. So, why do we have to integrate that? Because the motor model is the harmonic model is simply leakage inductance. So, the harmonic voltages are getting applied to the leakage inductance of the machine, and thus the corresponding harmonic current is proportional to the integral of the harmonic voltages. So, the current ripple is proportional to the integral of the error voltage vector. So, the integral of error voltage vector is what we call as the stator flux ripple vector, which is a measure of the current ripple vector, as we will see today. And we can use this to study the RMS line current ripple over a subcycle, and we will try reaching this point, and so further other things will be done in the next couple of lectures from now. So, first to have a review of this. So, today's lecture the focus is on analysis of line current ripple using the notion of stator flux ripple. So, we would have a quick review. So, this is the voltage source inverter, and you have two devices in every leg, they are switched in a complementary fashion. So, every leg is actually a single pole double throw switch. This is the pole, there are two throws. So, every leg is a single pole double throw switch, and this terminal is commonly called as the pole, and pole voltages are usually measured with respect to the DC midpoint. So, VRO for example is called the pole voltage, and VRY is the line to line voltage, and the load usually that we see is connected is like this RYB, star connected load, whose neutral N is not particularly connected anywhere, and this R to N for example is VRN. This we will regard as the output voltage, that is the phase voltage, output phase voltage of the inverter, and we would look at the harmonic spectrum of this. And firstly, if VRN let us say it has certainly a fundamental component, that is whatever gets applied here has a fundamental component and also has harmonic components. The fundamental component, which we can call let us say VRN1, sees the fundamental equivalent circuit of the motor. Then there are harmonics, and what do the harmonics see? Now, you can look at a quick review of this. So, the equivalent circuit looks like this. The harmonic voltages produce the synchronous frequency corresponding to the harmonics is very high, and therefore, the difference between that synchronous frequency and the rotor speed is very high, and therefore, the slip is close to 1. What you have is RR by S usually, and this slip is close to 1, and when you have the slip is close to 1, the slip, so this is a very small resistance now. In the case of fundamental component, the slip is very small, something like 3% or 5%. So, RR by S is a big number. Here S being almost 1, RR is a very small number now. So, and there is low resistance in the rotor circuit, and both these resistances RS and RR are negligible compared to the reactances omega LS and omega LR respectively at harmonic frequencies. So, the frequencies are very high, and therefore, the equivalent circuit reduces just to this. This is the magnetizing inductance, this is the stator leakage inductance, and this is the rotor leakage inductance. Now, you go one step further, this leakage reactance is much lower than the magnetizing inductance. So, this inductance is much lower than the magnetizing inductance, and therefore, the equivalent circuit can be further reduced here, and this is the harmonic equivalent circuit. This is what we had seen before now. So, every harmonic voltage sees basically this as the equivalent circuit, and therefore, the corresponding harmonic current is derived by dividing the harmonic voltage by the harmonic reactance, and the harmonic reactance is proportional to the order of this. So, 7th harmonic sees higher harmonic reactance than 5th harmonic. It is n times omega multiplied by Ls plus Lr. Therefore, higher harmonic voltages see greater harmonic reactances, and therefore, they for the same amplitude they produce lower amount of harmonic current. So, that is the idea now. So, this is what is given here. In is the nth harmonic component, and Vn is the nth harmonic voltage component, that divided by n omega L. Here that L is that sum of Ls plus Lr that I have taken the previous thing. So, this is the amount of harmonic current that would flow now. If you are considering something like let us say the 49th harmonic, then the corresponding 49th harmonic voltage, that divided by 49 times this reactance, that would give you the 49th harmonic current. And similarly, you can sum up all of this, that is all the harmonics etc. that you can sum up. This is sigma of In squared for n not equal to 1, which I should probably indicate there, that is with n not equal to 1, that is you leave alone the fundamental, you consider all the other harmonics, take their sum and divide it by I1, that is the what is called as the total harmonic distortion factor of the current waveform. The THD stands for the total harmonic distortion, and ITHD is the total harmonic distortion of that current waveform. And here yes, you can see component by component, if you can go In is what? Vn by n omega L. So, In is proportional to Vn by n, as you can see here. So, you can say that this is sigma Vn by n the whole square is a measure of sigma In square now, and that divided by V1 gives you the weighted total harmonic distortion factor of the voltage waveform, which is equivalent to the current THD. Now, what you can do is, if you want to calculate get a measure of the current THD, you can try and compute weighted THD. If you have to try and compute weighted THD, what you can do? You have to come up with Vn, or for ITHD you have to come up with every individual In, that requires every individual Vn. So, it means you have to compute the harmonic spectrum. So, that is one way of doing it now. So, you can compute individual harmonic voltages, and from there the individual harmonic currents, and therefore, you can get ITHD, or you can compute the individual harmonic voltages, and thereby you can compute the weighted THD of the voltage waveform. Now, if you look at it a little differently, now let me say this, I can write it as I tilde RMS, because what is that? This is the sum of all, this is sum of all harmonic currents, square of the harmonic currents now. And so, this what you have here is really the mean square value of the ripple current now, and if you take it under a square root, it becomes the ripple. So, there is the RMS ripple current, where I tilde RMS is the RMS ripple current divided by I1 is the fundamental current. I can get this and do this now. So, to calculate ITHD, one possibility for me is basically to try and evaluate I tilde RMS directly. So, can I evaluate I tilde RMS directly? Can I get a measure of I tilde RMS directly is a question now. That is what we will address. We will start addressing in this class, and we will probably complete in the next lecture, and so on. And we will also see how this I tilde RMS is influenced by different PWM methods. That is, when you consider different PWM methods, you are going to compare them at the same fundamental voltage. So, this is going to be the same, but the nth harmonic component is going to be different. Therefore, the nth harmonic current is going to be different, right. Therefore, what you have is this I ripple current is going to be different, or this Vn by n the whole square is going to be different. Let us say we are comparing conventional space vector PWM and a particular bus clamping PWM, or a particular advanced bus clamping PWM method. We would obviously compare them at the same V1. So, what will be different is the harmonic voltages will be different, and therefore, the harmonic currents will be different, and therefore, the current ripple or THD will be different now. So, we would try computing the I tilde RMS directly, instead of going from the through the frequency domain. We will approach the problem in the time domain or in the space vector domain, so to say, and we will try and evaluate this I tilde RMS, which is what we would look at today now. So, before that, let us just review a typical harmonic spectra of the inverter output voltage, which we looked at in the last class. So, let us say this is your frequency and this is the amplitude. This is the frequency and amplitude now. So, let me now draw a few different components. This is the fundamental component at F1, and the fundamental component is what I was trying to tell you. This depends on the DC bus utilization. This can be as high as, if you are talking in terms of peak phase fundamental voltage, this can be as high as VDC by 2 or VDC by root 3, and it can be anywhere between 0 and VDC by root 3, right. Then we are looking at PWM methods where the switching frequencies are much higher than the fundamental frequency. So, what we will have is, we will have the switching frequency here, and then you will have twice switching frequency and thrice switching frequency, and so on. So, you will have harmonic components here. You may have some harmonic components like this. You will have some harmonic components like this. So, this is the fundamental, and this is first side band, SB standing for side band. This is the second side band, and this is the third side band, and so on and so forth. And now, this FSW is the average switching frequency. FSW is the average switching frequency. So, what is that average switching frequency? If I talk of conventional space vector PWM or sine triangle PWM or any continuous modulation method, then that FSW is directly equal to the carrier frequency itself. It can be directly equal to FC itself now. If I talk of bus clamping PWM method, then the average switching frequency is 2/3 of the carrier frequency, that is what it is now. And then if you look at, let us say, the advanced bus clamping PWM methods. So, what happens is, in some regions it switches, in some regions it does not switch. So, in some regions it switches, let us say, at a nominal frequency, and in some regions at double the nominal frequency, and some regions it is 0, and therefore, you have what is called as the average switching frequency, and you get for all the advanced bus clamping PWM methods, you get them, you get their sidebands like this now. So, the other way you can also find out in some cases that it is the carrier frequency here. This is FC, 2FC, 3FC. This may be a little confusing usually. So, let me say a few more words on this now. So, let me say I take sine triangle PWM, that is what we discussed first. So, the carrier frequency is FC. So, this is your carrier frequency, and then around the second and then the third harmonic, it so on, it produces that. So, you take any, instead of sine you had third harmonic component also, you will have your sidebands happening around FC, 2FC and 3FC. The amplitudes of these components will change now. That is, when you add third harmonic component, for example, of 1/4 third harmonic, there is certain amount of variation that you get in the harmonics, and it, the harmonic properties improves now. So, you get them around FC, 2FC, 3FC, etc. now. So, if let us say you use triangle comparison PWM, and you use something like bus clamping PWM, in bus clamping PWM, this carrier frequency, if it is 3 kilohertz, the corresponding switching frequency is only 2 kilohertz. So, in that case also you should actually take it as FC, 2FC and 3FC. So, that was the advantage I was mentioning the other day. If you want to compare, let us say, conventional space vector PWM and bus clamping PWM at the same average switching frequency, then what happens is, for bus clamping PWM your carrier frequency can be increased to 1.5 times. So, if you are talking of 2 kilohertz switching frequency, so for conventional PWM, the corresponding carrier frequency is 3 kilohertz for the bus clamping PWM. So, there is a shift, the first sideband shifts by 1.5 times, and therefore sees a higher harmonic reactances, and therefore better filtering of the components is what, as I mentioned before now. So, if you are talking of these kind of bus clamping methods, conventional space vector or sine triangle PWM, then you can say this FC, 2FC, 3FC are where you have all the sidebands around now. And if you are talking of the conventional space vector or sine triangle PWM, etc., all the continuous PWM, in those cases FC and FSW are equal, the switching frequency, because it switches at uniform frequency throughout the line cycle. So, they are the same, there is no confusion. And if you are talking of advanced bus clamping PWM, then FSW is the average switching frequency, 2FSW is the twice the average switching frequency, 3SW is the three times the average switching frequency. So, this is what I would like to tell you now, but nevertheless, this is the typical spectra. So, you have fundamental component and there is a large separation here, this can be 50 hertz and this can be something like 5 kilohertz or so, there is a large separation between these two frequencies now, and therefore, it is possible that you can develop separate analytical methods for this component and those components, which is what we are doing now. So, one approach is to calculate all the individual harmonic components, which has been done before, and from the individual harmonic components find the corresponding harmonic currents and then calculate the ITHD you want. But as I mentioned, what we are trying to do is, we are not trying to go by this route, we are trying to see if we can come up with the I tilde RMS more directly. So, you have this references, as I mentioned. If you are looking at sine triangle PWM about the frequency spectrum, you can find it in textbooks such as the book by Professor Mohan. And then, as I mentioned, if you are looking for the amplitude, the frequency spectrum and what are the various amplitudes of these components corresponding to conventional, or continuous and discontinuous PWM methods. Continuous and discontinuous PWM methods, continuous such as sine triangle PWM or conventional space vector PWM. Discontinuous PWM methods such as 60° clamp, 30° clamp, etc. You could probably look at this book or quite a few papers in this area, where they use the idea of double Fourier series to calculate these. So, you could consider that now. And if you want to compute those harmonic components like this for advanced bus clamping PWM, then the reference you should look at is the PhD thesis by Dr. D. Zhao, space vector methods for AC drives to achieve high efficiency and superior waveform quality. and submitted to the Arizona State University. So, this is a PhD thesis which actually discusses the harmonic spectra of advanced bus clamping PWM methods and how you can calculate those amplitudes using what is known as the Fourier theory of jumps. So, these are useful references for you if you are interested in the amplitudes of the individual harmonic components. Now, let us move on. Now, in the harmonic spectrum we have some important features, as I mentioned, that is what we would focus on: the fundamental component, dominant first sideband, dominant second sideband component, and the weighted total harmonic distortion factor of the voltage waveform. So, these are what we would call as. So, the first three are the important features, and the fourth one is actually a it is what is computed out of all the harmonics, all the or that are relevant and significant there now, right. Then let us say we go down. So, if you look at the dominant sideband harmonics, we had already discussed about the fundamental component, that is the DC bus utilization. So, PWM methods in general, for given a DC bus voltage VDC, can produce peak phase fundamental voltages up to VDC by root 3. And if you want to compare the first and second sidebands, you see certain features. If you are talking of conventional space vector PWM, that is what I abbreviate as CSV PWM now, you find that the second sideband is dominant at low modulation indices. If you are looking at low modulation indices, that is when the fundamental voltage is low, not really close to VDC by root 3, but something let us say VDC by 2 root 3 or something of that sort. Instead of 0.577 VDC, you are looking at 0.2 VDC. So, at such low modulation indices, you will find that the second sideband is dominating. So, what happens if the second sideband is dominating? So, the second sideband sees a leakage reactance roughly twice that as seen by the first sideband, and therefore, the harmonic currents are much lower for the same amount of harmonic voltage amplitudes, and therefore, conventional space vector PWM has a low harmonic distortion at low modulation indices, whereas at high modulation indices you find that its first sideband dominates. So, the leakage reactance seen by the first sideband is lower, and therefore, the harmonic currents are higher, the ripple current is higher now. The contrary, the other situation is converse situation is seen in case of advanced bus clamping PWM. There you find that the first sideband dominates at low modulation indices and the second sideband dominates at high modulation indices. Therefore, what happens at high modulation indices? Second sideband dominates and they get filtered better. The harmonic amplitudes may be substantial, voltage harmonic amplitudes may be substantial, the corresponding current amplitudes are low, and therefore, your RMS current ripple is low. And therefore, you will find when you compare CSV PWM and advanced bus clamping PWM, you will find that the CSV PWM is better at low modulation indices, whereas advanced bus clamping PWM you will find that they are better at high modulation indices now. So, I am giving you a particular reference, that is T. Bhavsar and G. Narayanan, harmonic analysis of advanced bus clamping PWM techniques. So, this paper actually gives a comparison of the dominant sideband components of conventional space vector PWM and advanced bus clamping PWM. It also gives some dominant components of for the bus clamping PWM methods, right. So, after this review, so we had just looked at all the Fourier in the harmonic spectrum. Now, let us try and see how we can do the same job in the space vector domain. So, this is now in the space vector plane and you have this angle and we are going about that, and this is a revolving vector and we are going to sample it every time, and if the sample falls in active vector in the sector 1, we will use active vector 1, active vector 2 and null vector to produce this average vector. So, if this is what you get, active vector 1, active vector 2 and null vector now, and they have to be applied for times T1, T2 and Tz. How do you calculate T1, T2 and Tz? Like what I have shown here, V1, T1, V2, T2. So, this is the volt second balance, and T1 is equal to Vref sin 60 minus alpha Ts divided by VDC sin 60. Similarly, T2 is proportional to Vref sin alpha. So, it is Vref sin alpha by VDC sin 60 Ts, and Tz is Ts minus T1 minus T2. This is how you calculate the dwell times for the active vector 1, active vector 2 and the null vector, as I have said in the previous lectures as well. So, now when you do this in conventional space vector PWM, what do you do? The null vector you use both the null states. The null vector can be applied using two different 0 states, minus 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 wherein all the bottom devices are on and plus 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 wherein all the top devices are on. So, let us say you start from minus minus minus, so all the bottom devices are on, you switch R phase after Tz by 2 seconds and you reach here plus minus minus, this is active state 1. You stay here for T1 seconds and then switch Y phase and reach here, that is plus plus minus active state 2. you stay here for t2 seconds and after that you switch the B phase and you reach here and you stay here for remaining Tz by 2 seconds. So, at plus 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 now, and you would do the reverse in the next subcycle. This is conventional space vector PWM. We are now going to take this conventional space vector PWM as a specific example for trying to evaluate the RMS current ripple in the motor when for evaluation of RMS current ripple. So, we are going to look at a induction motor drive, and an induction motor drive operated using a voltage source inverter switched using conventional space vector PWM and try and understand how its RMS current ripple would vary, right. So, here we go. So, now what is to be done first? There is this error voltage vector. Why is there a ripple current? Firstly, it is because there is a difference between what you need and what you apply. There are harmonic currents, there is ripple current. The ripple current you can say is the sigma of all the harmonic currents. Why is there a harmonic current? Because there is certain harmonic voltage. So, there is a difference. So, the voltage that you need is sinusoidal, but inverter's output is not exactly sinusoidal. Therefore, there are ripple, there are harmonic voltages and correspondingly harmonic currents. So, what you can now look at it, the same thing you can look at it in the space vector domain now. This Vref is what you want to have. So, you are trying to, instead of 3-phase sinusoidal waveform, you are trying to apply a revolving voltage vector of magnitude Vref and revolving at a frequency omega. So, this is Vref at a particular instant, here it is Vref now. At this instant, you can't apply this Vref vector because the inverter does not produce this Vref vector. What are the vectors it produces? The inverter produces a null vector and around 6 active vectors here, and those 4 active vectors are not very useful here. These 2 active vectors are the ones which are the closest to that now. So, what you are trying to do is, in this over a small subcycle duration, you are trying to apply this null vector and these 2 active vectors, and by time averaging you are trying to produce an average vector which is equivalent to Vref. The instantaneous vector is at any instant of time either null vector or active vector 1 or active vector 2, and it is never equal to the reference vector itself, and it cannot be. So, now let us say you have the required vector is Vref vector, but the applied vector is null vector. So, what do you have? What is getting so there is an error vector. What is that error vector equal to? That error vector is equal to minus V reference vector. So, let me just write it down. So, let me call this as V error vector. This is V error vector, that is equal to minus V reference vector. So, this is in a particular subcycle and during whenever the null vector has been applied now. So, you can also resolve this vector along the alpha axis and the beta axis now. Let me say, I would say V alpha tilde, let me call this is the error along that. So, what is the voltage applied along the alpha axis? Nothing, because it is null vector. So, 0, and what is the reference value? It is Vref cos theta s. Just note that I am just using theta s here instead of alpha, just so as not to confuse with this alpha axis and beta axis. Okay. So, what you have here is V alpha tilde is equal to minus Vref cos of theta s. There is an error between the applied voltage and the reference voltage. The applied voltage is 0 vector, and this is 0 vector minus V reference vector. This is actually 0 vector minus V reference vector. It is basically minus V reference vector. So, what is V alpha tilde? It is 0 minus Vref cos theta. Similarly, what is V beta tilde? That is the error voltage along the beta axis. This is minus Vref sin of theta s. And you can see that it will vary when you go to different sectors. So, V alpha tilde and V beta tilde are vary, and they will vary from sector to sector now, right. So, now let us say we look at the other error voltage vector when active vector 1 is applied. You have applied active vector 1. So, now the V error vector is V1 vector minus V reference vector, is V1 vector minus V reference vector, and that is what is given as this V error vector here now. This can be resolved along alpha and beta. So, let us say I take V alpha tilde. So, what is the applied voltage along alpha axis? The applied voltage is V1. So, that is VDC, it is entirely aligned along the alpha axis, therefore, it is VDC and minus V reference cos of theta s. This is the error voltage along the alpha axis. Similarly, you can consider the error voltage along the beta axis, and the what is the applied voltage vector along the beta axis? That is 0, because the applied voltage vector 1 has no component along the beta axis. This minus V reference multiplied by sine of theta s. So, this is what it is in the alpha axis and this is what it is in the beta axis now. So, when the applied voltage vector is active vector 2, you once again have an error voltage vector. What is that error voltage vector? V error vector is equal to V 2 vector minus V reference vector, and this V 2 vector is nothing but VDC angle 60 degrees. This is the same angle as VDC angle 60 minus V reference, and you can say this V reference angle is theta s. And for just for clarity, I am writing V 2 and V ref in terms in the polar coordinates, so that we are also a little clearer now. Then your what is the V alpha tilde? V alpha tilde is whatever is the voltage applied along the alpha axis, that is VDC cos 60. So, that is going to be VDC by 2 minus V ref cos of theta s, and the error voltage along the beta axis is the applied voltage along the beta axis, which is root 3 by 2 times VDC minus V reference sine of theta s. So, these are the error voltages that you get along the alpha axis and the beta axis. So, you can integrate these error voltages to get the measure of the current ripple along alpha axis and beta axis. So, now you can see that these quantities kind of go on varying, that is you will have to do this over the entire all the 6 sectors now, and we will see that we will go into, instead of alpha and beta, we will look at the DQ reference frame, and in the DQ reference frame we can come up with a procedure which in where there is symmetry about every sector. It is enough if you do the calculations over every sector. So, it is actually from alpha beta we have been looking at the space vector plane here, that is in the stationary reference frame, that is this is the alpha axis and this is the beta axis, though alpha and beta are missed out here. So, you have alpha and beta, this is the stationary reference frame now. So, the reference axes are fixed now. One can also consider reference frames, I mean where the reference axes are rotating. For example, one can consider a frame where the reference axis is attached to this V ref vector and keeps rotating. In every it keeps rotating like this now. So, that is a we can consider a synchronously revolving reference frame now. So, let us say you have the alpha axis and you have beta axis, and then you have what is called as a DQ reference frame. So, you have a synchronously revolving reference frame. This axis is called D axis or direct axis, and this can be called Q axis or the quadrature axis. And let us say you have D and Q, and there is an angle phi coming between these two. So, you can consider a different thing and you can go about defining a transformation now. So, what you can do is, let us say you have V alpha, V beta and you need Vd. Let us say Vd can be written in terms of V alpha and V beta. So, this is Vd is equal to V alpha times cos phi. Is it all right? So, then let us say there is some V beta plus V beta times cos of 90 minus phi or sin phi. So, if you know V alpha, V beta and the angle phi between the two, you can compute what is Vd. So, then you can also compute the voltage along the Q axis. So, what is that? If it is V beta, it is very clear, that is going to be V beta times cos phi. And what is V alpha? So, here you have V alpha, and V alpha sin phi is going to be something in this direction and it is opposite to the Q axis. So, this is minus V alpha sin phi plus V beta cos phi. So, this is what you can call as a transformation from the stationary reference frame to a synchronously revolving DQ reference frame, where if you have the components alpha and beta. So, the 3 phase quantities Vrn, Vy and Vbn, let us say, has already been transformed into V alpha and V beta. These can be further transformed into Vd and Vq by doing this. That is what we are trying to do here now. Or let us say you have 3 phase currents IR, Iy and Ib, they have been transformed into I alpha and I beta. These can be further transformed into Id and Iq as shown here now. So, that is what you can do, that is using this transformation. Now, you can write this transformation in a matrix form. Vd Vq is an array, and then cos phi sin phi minus sin phi cos phi is the transformation matrix, and multiplied by an array V alpha V beta, that is what you can do. And this matrix cos phi sin phi minus sin phi cos phi is a unit matrix, right. So, I mean its determinant is unity, it is easily invertible. So, it is cos phi minus sin phi sin phi cos phi would be the inverse of the matrix. If you use the inverse of the matrix, you can compute V alpha and V beta using Vd and Vq. So, this transformation is reversible. So, you can have V alpha V beta and the angle phi, and you can get Vd and Vq. On the other hand, you can also have Vd and Vq, and you can have phi is given to you can compute V alpha and V beta. So, this is the stationary to synchronously revolving reference frame transformation and its inverse that you can really see from there. I am not writing down the inverse, but it is very easy for you to write it down yourself now. So, I am doing this primer now. For example, we have been doing this with this definition of D and Q axis. Let us go and continue with our study on the error voltage vector, which is what we have been looking at today now. So, now I would want the D and Q axis. Now, I am going to do the analysis, the same error voltage vector, but I am going to try and resolve them in the synchronously revolving reference frame now. So, what I can first do is I can take this as one of the coordinate axis, this reference vector that I have here as one of the coordinate axis, one of the revolving axis now. And since this is the applied voltage vector, and so I can call this as Q, and it revolves at this synchronous frequency omega, and the D axis is going to be 90 degrees behind that. So, if you consider an induction motor, so if this is the voltage applied along the Q axis, the stator voltage vector is applied along the Q axis, then the flux is along the D axis. So, that is also the reason for our convention calling this as Q and calling this as D, right. So, I am just defining this as Q axis and D axis, alright. So, now I can write the same error voltage vectors, the error voltage vectors are still same, right. For example, here you have V error, this is your V error, this is V error corresponding to active vector 1, when active vector 1 is this is applied now. So, if I can write down instead of V alpha and V beta, what I can do is I can write down this as V Q tilde. This is the error voltage along the Q axis. What is the error voltage along the Q axis? That is the component of this applied along the Q axis. So, what is the applied vector is VDC angle 0. So, along the Q axis it is VDC times cos of theta s, that is what it is, and this is the applied vector minus the actual vector, the actual thing is V reference. So, this is the error along the Q axis now. Similarly, you can define the error voltage component along the D axis. How is that? The applied vector, how much is the applied vector? It is VDC times sine of theta s minus 0, just to make it obvious. There is no, I mean the reference vector is entirely along the Q axis and it is not along the D axis. So, your Vd tilde is actually VDC sin theta s minus 0. This is the error voltage vector when you consider an active vector 1 to be applied here now. So, similarly, if you consider a situation where you are considering the active vector 2 to be applied, right, when you consider the active vector 2 to be applied. So, you can once again come up with this. So, this is the error voltage vector. This error voltage vector we had earlier expressed in terms of the alpha axis and the beta axis. Now, we can express that in terms of the D axis and the Q axis now. Okay. So, this is the Q axis and this is the D axis, and this is 90 degrees here. Okay. And what is the error voltage along the Q axis? That is VQ tilde is equal to the voltage, applied voltage along the Q axis. Now, the applied voltage has a magnitude VDC and its component along the Q axis is VDC cos of 60 minus theta s. This is the applied voltage minus V reference. So, VQ tilde is VDC cos 60 minus theta s minus V reference, and there is also error voltage component along the D axis. What is that? The error voltage, the applied voltage magnitude is VDC, right. It has actually a component like this. So, that is VDC sine of 60 minus theta s. This is in the direction opposite to D axis, and therefore, we have minus VDC sine of 60 minus theta s. So, this is VQ tilde and this is VD tilde, right. So, we earlier saw how you can do it in the when you with the error voltage vector, we are trying to express it in the DQ reference frame when active vector 1 is applied, instead when active vector 2 is applied, you can do this. Similarly, when null vector is applied also, it is much simpler. When null vector is applied, it is simply equal to VQ tilde is minus Vref, that is all, and VD tilde is 0, that is what it is, and which I have not stated here, right. So, let us say we go further, excuse me. Yeah, so this is a previous case where we can probably look at that. So, we just for completeness, let us finish that also. So, that here what you have is VQ tilde is what is applied is 0 minus V reference. So, VQ tilde is minus V reference, and VD tilde, the applied voltage vector is null vector. So, it has no component along either d axis or q axis. So, it is 0, and the reference vector also has no component along the d axis. So, VD tilde is simply 0. So, this completes our error voltage vector study in the alpha beta domain and also in the DQ domain. So, this is the error voltage vector corresponding to null vector, and this is the error voltage vector corresponding to active vector 1. This is the vector corresponding to active vector 2, right. So, what is the next step? We should go about integrating this error voltage vectors. That is what we have to do. We have to go about integrating this error voltage vectors to get a measure of the line current ripple, because as far as the ripple voltage is concerned, the machine is seen as a leakage inductance. Therefore, the integral of the voltage is proportional to the current, right. So, this is stator flux ripple vector. What is stator flux ripple vector? As I mentioned to you, this is the integral of the voltage error vector. Now, I have not drawn anything, I have just given the same vectors. This is you have your Vref vector of magnitude Vref and angle theta is measured from the alpha axis. This is your desired reference vector to be produced in a subcycle. You are going to be doing this by applying active vector 1 for t1 seconds, active vector t2 for t2 seconds, and null vector for tz by 2 seconds. And you are going to do this by employing the conventional switching sequence, where you would apply this 0 state minus 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 for tz by 2 seconds, and the active state plus minus minus for t1 seconds, then plus minus minus for t2 seconds, and finally plus 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 for tz by 2 seconds now. So, let us do the job now. So, what we do is now let us just do an integration of the error voltage vector. We looked at the error voltage vector when a particular thing is applied. Now, we are going to look at the error voltage vector and its integral over a cycle, over a subcycle. Okay. Let us just start with this now. So, let me call this as q axis. Let me just draw that. Ignore drawing inaccuracies. It is just a straight line, the same which is connected to the reference vector, and this is the d axis, and this angle is 90 degrees. Okay. Right. Now, this is here. What I can say is, for convenience, let me say, let me not draw the d axis here, let me draw the d axis here, correct. So, I am just drawing the DQ reference frame, and this is the origin point now. So, let me now go into the next step. So, what I have is, I have this kind of reference vector. I am going to produce an average voltage vector equal to the reference vector. So, what I first do is, I apply the null vector minus 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 for certain seconds tz by 2. So, I start from here. The error voltage vector is like this, and therefore, the integral of the error voltage vector is going to grow like this. It will grow like this. So, the error voltage vector is constant, and what is its magnitude? It is equal to minus V reference vector. It is equal to minus V reference vector. And what you are trying to do is, you are integrating minus V reference vector here when you apply it here, and at the end of 0.5 tz seconds, you have reached something like this. You have reached something like this. Okay. Now, 0.5 tz is over. What is the next state to be applied? Plus minus minus. What is the reference vector? It is the same V reference vector. What is the error voltage vector? Now, this is the error voltage vector. So, what is going to happen is, you will have something which is parallel to this line. You will have something parallel to this line, and so this will go on. You will have something parallel to this line. So, this is the error voltage vector, and this is the error voltage vector. You are integrating that. So, it will move along this direction. This direction is parallel to the error voltage vector corresponding to active vector 1. So, you have reached here now. So, here at the end of this, this is 0.5 Tz plus T1 you have reached here now. At the end of this you are applying the active state 2 and the corresponding error vector is like here. So, it is going to move like this and in this direction, it is going to move in this direction. When active vector 2 is applied, it will start from here and it will move here and finally, it will reach here at what instant 0.5 Tz plus T1 plus T2. Then from here it will move back when you are applying the 0 state 7 and it will go back to the origin. It has to go back to the origin. Why? Because of volt second balance. So, Vref vector into Ts is equal to the average voltage vector multiplied by Ts. What you are trying to integrate is the error voltage. So, the average error voltage over a subcycle is equal to 0 and therefore, whatever you start from you get back there. So, this is what is the stator flux ripple vector. Now, this is actually a vector. This is actually a vector. Let me use some different color here and let me call this as a vector now. And this has certain we can call this by some psi and tilde. So, the psi tilde vector has its magnitude goes on changing. So, initially if you look at it, its magnitude is 0 and its magnitude is increasing and the angle is not changing now when the null vector is applied. It is increasing along the q axis and the negative q axis to be precise now. From that particular point what happens when 1 is applied, both its magnitude and angle start changing, its magnitude and angle start changing and go up to this point here. But its tip is moving, but its tip is moving at a pace. What is that pace at which it moves? That is equal to the magnitude of this error voltage vector. Whatever is this V1 vector, it is its magnitude at which it got. When it was moving here, the speed at which it is moving is proportional to this magnitude of the error voltage vector, that is minus Vref, and here this speed is proportional to this error voltage vectors. And when you reach here, it is 0.5 Tz plus T1 and from 0.5 Tz plus T1 T2 vector is applied, vector V2 is applied for time T2 seconds and it moves here, it moves at a constant speed and this speed is proportional to this magnitude of the error voltage vector, which is then it goes and reaches here and finally it goes back here and reaches this now. So, this psi tilde vector is a measure of the current ripple vector, that is this error vector that you are considering here, you can consider that as the 3-phase transformation, the 3-phase to 2-phase transformation of the space vector, of the ripple, that is in every phase you have harmonics, the sum of all the harmonics is ripple and the 3-phase voltage ripple can be transformed into the space vector domain and that is the voltage vector now. When you integrate that voltage vector, you get the stator flux ripple vector, which is a measure of actually the current ripple vector now. So, this is actually a measure of the 3-phase ripple currents transformed into the space vector domain. So, this is what it is a measure of now. So, it has got a triangular trajectory, this vector has got a triangular trajectory and you can see that every side of the triangle is proportional to the error voltage vector. The base of the triangle, which is along the q axis, is parallel to the error vector corresponding to null vector and this side is parallel to the error vector corresponding to vector 1 and this side is parallel to the error vector corresponding to vector V2. So, the next thing that you can do is get into further analysis. We can try and resolve this along the d axis and the q axis components and see how it goes about here now. So, let me just try reproducing that figure roughly. Okay. Now, let us say this is the q axis and this is the d axis we had in the previous graph and let me just draw the vectors that you really had there. So, this is when 0 state 0 is applied, this is when 1 is applied, this is when active state 2 is applied, this is when 7 is applied now. So, you can resolve this vector into the d and q axis components now. So, let me once again write the psi tilde vector also. So, this is called as psi tilde vector now. Okay. So, let me draw the axis, this is let us say the time axis and let us say this is my psi q tilde, the q axis component. What happens? This is 0 and the q axis component changes like this. It becomes negative and negative when 0 state is applied. This is when the 0 state is getting applied. So, it reaches some value like this now. Subsequently, the active state 1 is applied. During that time, you find that this is the line. When you go around this line, you have see that it becomes less negative, that is, it starts moving towards the positive direction, and at this point it is crossing the, it is becoming positive and like this. So, I can say it increases like this. And when I am applying the active state 2, you can say that the psi q is more or less equal. I am sorry about that. This is not there. There is no blur here. Let me redraw that. Okay. So, it is more or less flat here. And finally, when I apply the active state 7, it goes back to 0. It goes back to 0. Let me extend this horizontal line. So, this is the entire subcycle time T s. So, this region is T z by 2, this duration is T 1, this duration is T 2, and this duration is T z by 2, and the states applied are 0, 1, 2 and 7. So, this is one component of, this is how one component, namely the q axis component of the current ripple vector or the stator flux ripple vector changed now, right. Then I can plot the psi d tilde vector, and the psi d tilde vector is, during the initial time it is 0. When 0 is applied, it does not change at all. Again when 7 is applied, it does not change at all. In between the two, what happens? It goes about increasing. It reaches a peak when at the end of this interval T1 and the start of interval T2, and then it falls linearly here. So, this is what it is now. So, this is how the d axis ripple varies. So, there is the q axis ripple and there is the d axis ripple, and you can also equivalent, these are also equivalent to iq tilde and id tilde. It is just a question of scaling them, iq tilde and id tilde. So, if you can calculate this iq tilde and id tilde, now what you have them is, you have the ripple quantities in the q axis and d axis. What you need to do is, you use the inverse of this stationary to synchronous reference frame transformation, that is from synchronous to reference frame to stationary reference frame. You can go to I alpha tilde and I beta tilde, and from there you can actually move on to IR tilde, IY tilde and IB tilde. So, you can, thus it is possible for you to compute your ripple. That is what I am trying to evaluate. So, I am just driving you there, it is kind of trying to take you through the steps now. So, this is the initial step. I am just trying to give an indication of how exactly we can reach there. So, it is possible for you to get IQ tilde and ID tilde as they vary, and from IQ tilde ID tilde you can use transformations I alpha tilde, I beta tilde, IR tilde, etc. It is possible to come up with, alright. So, this is how it varies, and IQ tilde and ID tilde have their own significances too. That is, both of them contribute to the current ripple. As we will see later in the module on pulsating torque, IQ tilde affects the torque pulsation much more than ID tilde does. So, that is something that we will look at in the next lecture. So, we will just try and do some things more now. So, what is that? So, we are just trying to understand this ripple. So, you can see that the ripple starts from 0 and ends from 0. You look at both the components are 0 at the start as well as ending, and the d axis ripple does not change whenever the null vector is applied. So, that is actually one of the benefits by aligning this. See, this q and d axis should be revolving, but we made sure that the q axis is aligned with the reference vector and the d axis is in quadrature with that. By making the q axis aligned with the reference vector, we have made sure that it has no component along the d axis. That is what has given this advantage. Vd tilde is 0 is in these intervals, and so it is kind of easier to calculate now. So, this you can say is the instantaneous stator flux ripple along the d axis and q axis, and this also gives you the instantaneous q axis and the d axis ripple now. So, for now, let us say if you want to go to the RMS value, how can you compute the RMS value is an interesting question now. I will just try to look at that question. Now, I will just start off with one of them, namely let me just take a different color now. So, I want to calculate psi d tilde, RMS value of psi d tilde. What can I do? I can just square this. So, if I square this, 0 squared is 0. Again, if 0 is squared, it is 0. Now, this linear portion if I square, it is going to become a parabola like this. It is going to become a parabola like this. Again, this linear portion if I square, it is going to become a parabola like this. And what I need to do is I need to compute the areas under these parabola. I need to compute the areas under these parabolas. How can I compute the area under these parabola? There is some simple ways are available. So, let me just choose yet another color here. Let us say, now let me say there is a rectangle. So, this is a rectangle, again this is another rectangle. So, the area under the parabola like here is 1/3 of the area under this rectangle. Is that right? This is a property under parabolas. Now, we will discuss about this a little more probably in the next class in a slightly more relaxed fashion. And again, if you look at the area under this parabola is equal to 1/3 of the area of this rectangle. It is not very difficult, because you can see that in the parabola, if you look at this, y is equal to x squared is what you have the equation for a parabola. So, if you are trying to integrate it from 0 to x like this, y is equal to x cube, and you are trying to integrate in this area. So, you will see that the area is x cube by 3. This area is x cube by 3. And what is the total area? So, this is let us say x, this is x squared. So, the total area is x cube. So, the area of rectangle is x cube, and rectangle is as an area equal to x cube, and the shaded area is x cube by 3. Thus, you can see that the area under that is 1/3 of that. So, I am just trying to use that idea to calculate this now. So, this is not necessarily when it is 0, this may be some x1, this may be x1 squared, and you can come up with that now. Let us say you are not you are having a parabola which is sitting not really there, but it is sitting somewhere like this. This is the axis, this is the horizontal axis x, this is the vertical axis y. The parabola is touching here, I mean just there is a drawing inaccuracy, parabola value is equal to 0 at that point now. So, now let us say I want to compute the area here. This area is equal to 1/3 of the area of this rectangle. If I call these points, let us say A and B, and call this as C and D. So, the shaded area ACB is 1/3 of the area of the rectangle ACBD. That is all that I am trying to say now. So, that the parabola may be wherever it is. So, why are we interested in this kind of a parabola? If you actually multiply any straight line this and square that straight line, this is the kind of parabola that you are going to get. So, what you are actually having is you are having a straight line, and let us say you have a straight line like this. If the straight line is squared, you will get a parabola like this. That is a parabola which will have equal roots, real equal roots. That is how it is going to be. So, for those kinds of parabola you can calculate the area like this, and so we would go into this, and it is possible to do the calculations over a subcycle and try to compute the RMS value over a subcycle. So, we will do this kind of exercise in greater detail in the next class. Before that, I may anyway just indicate some references where these kind of calculations have already been done for you. So, these are the two papers where you can probably, there are some on other two papers also where these kinds of calculations have been done. The next lecture we will do this calculation of RMS current ripple over a subcycle in a greater detail, and we will also look at how this RMS current ripple is influenced by the PWM method or the switching sequence used. Thank you very much for your interest. I will look forward to your participation in the next lecture. Thank you very much.